Okay, student, good morning to all of you. So today we will start with linear simple harmonic motion. So very first we will give you the definition of linear simple harmonic motion. What is linear simple harmonic motion? Linear simple harmonic motion is motion of an object along a linear path in which the restoring force acting on the particle is directly proportional to the displacement of the particle from its mean position, and it is always directed towards the mean position and opposes the displacement or acceleration. So how to give the definition of linear simple harmonic motion? It is to and fro motion of an object along a linear path. To and fro motion of a particle along a linear path in which the restoring force that is called as F or acceleration is number one, directly proportional to the displacement of the particle from its mean position. And secondly, it is directly proportional to the displacement of the particle from its mean position and always directed towards the mean position and opposes the displacement. So this is proper definition of linear simple harmonic motion. What is linear simple harmonic motion? Linear simple harmonic motion is to and fro motion of any object along a linear path. Suppose object is moving along this linear path. This is A, this is B, and this is the extreme position O. So if the particle is moving to and fro along this linear path and the force or acceleration acting on the particle is always opposing the displacement. This is the direction of force and this is the direction of x. So here force is opposing the displacement. This is why it is called as restoring force. So to and fro motion of an object along linear path in which the restoring force or acceleration is directly proportional to the displacement of the particle is called as linear simple harmonic motion. Now, what are the examples of linear simple harmonic motion? There are two types of example. Number one, the motion of a simple pendulum. Motion of simple pendulum for a very small amplitude. If the amplitude of the simple pendulum is very small, then its motion can be treated as linear simple harmonic motion. Secondly, the motion of a spring pendulum. Motion of a spring pendulum. Or third example I can give you, the motion of a liquid, you can say mercury, in the arms of a U-tube. Arms of a U-tube. For example, this is simple harmonic motion. This is simple pendulum. If the amplitude is small, then it is simple pendulum. Spring pendulum. Spring pendulum is like this. Suppose it is a spring, and with the spring certain mass is attached. So this mass is moving up and down. This is a spring pendulum. This is a spring pendulum. So these are the example of. Similarly, third one is, this is first, this is second, and third one I can give you. If we have a U-tube, and in this U-tube, if we have kept any liquid, so in the liquid or in this U-tube, liquid will perform up and down motion. This is also called as linear simple harmonic motion. So I hope you all must have understood the concept of linear simple harmonic motion. Motion of a particle along a linear path in which the restoring force or acceleration is directly proportional to the displacement, but always acting towards the mean position, is called as linear simple harmonic motion. Now the second point of this linear simple harmonic motion which I want to discuss today is differential equation for linear simple harmonic motion. So let us start with differential equation of linear simple harmonic motion. Let us derive the differential equation for a linear simple harmonic motion. Dear students, just we have done for linear simple harmonic motion, we have restoring force Fr. Fr is directly proportional to minus x, where Fr is restoring force, Fr is restoring force, and x is displacement. So you have seen for linear simple harmonic motion, the restoring force is directly proportional to the displacement, but it is acting in the opposite direction. That is why we have minus sign. Now we can replace this proportionality. After replacing this proportionality, you will get Fr is equal to minus k into x, where k is constant and it is called as force constant. So it is force constant. This you can take as equation number 1. Now, according to Newton's second law, according to Newton's laws of motion, Newton's law, the restoring force Fr can be also given as m into A, where m is mass of the particle performing linear simple harmonic motion, performing linear simple harmonic motion, and A is acceleration. So force Ma is equal to, this is equation 2. Now from equation 1 and 2 we have, from equations 1 and 2 we have, you will get m into A is equal to minus k into x. This we can take as equation number 3. Now after equation number 3, I can just derive the differential equation in a very easy way. Let us see. After equation number 3 we have, as we know that acceleration A is second order derivative of displacement with respect to the time. Acceleration A is equal to d2x upon dt square. This thing you have done or you will do in your mathematics. Acceleration is second order derivative of the displacement. Therefore, from equations 3 and 4 we get, what do we get? Let us see. This you can write n into d2x upon dt square is equal to minus k into x. Now dividing both sides by m, you will get d2x upon dt square is equal to minus k upon n into x. Bring right hand side to left hand side, you will get d2x upon dt square plus k by n into x is equal to 0. This we can take as equation number 5. In equation number 5, this constant k upon n is taken as omega square. It is constant. Therefore, we will get d2x upon dt square plus omega square x is equal to 0, and this is differential equation. This is differential equation for linear simple harmonic motion. This was our aim, to derive the differential equation for linear simple harmonic motion. So it's very easy, you can just see it. For linear simple harmonic motion, we have restoring forces directly proportional to the displacement but acting in opposite direction, therefore we kept negative sign. So we got this proportionality we replaced by the constant, so Fr is equal to minus kx is as equation number 1, where k is force constant. But according to the Newton's law of motion, force is mass into acceleration. So we have two equations for force, equation 1 and equation 2. Left hand side of both equations are equal, so equating their right hand side we get equation number 3. Now this equation 3, acceleration is second order derivative of the displacement, that is A is equal to d2x by dt square. By putting this value of a from equation 4 in 3, we get m d2x by dt square is equal to minus kx. On solving, we will get d2x by dt square is equal to minus k by m into x. Bring this negative term from right to left, make it positive. Right hand side will become 0. Replace this k by m is equal to omega I square and get the final expression for the differential equation as d2x upon dt square plus omega I square x is equal to 0. Now one more small concept I would like to explain. What is force constant? What is force constant and its SI unit and dimensions? Force constant is K. As you have seen, the omega I square is equal to K by M, or in linear simple harmonic motion, we have seen force Fr is equal to minus K into x. From this equation, we can have, let us see, we can have the formula for K. What formula for K we will get from this equation? From this equation, we should have, therefore, K is equal to minus Fr upon x. Or you can write K is equal to magnitude of Fr upon x. If we are taking in magnitude, this is magnitude. This you can take as equation number 1 and this as equation number 2. From equation number 2, we can give you the definition of restoring force constant. This you can write Fr upon x also. Therefore, restoring force per unit displacement. Restoring force per unit displacement in linear simple harmonic motion is known as force constant. The definition of force constant is, it is restoring force acting per unit displacement. Means after moving 1 meter displacement, what is the force acting on the particle? That is called force constant. What is SI unit of force constant? SI unit of force constant, K is equal to, it is force, that is Newton, upon displacement, that is meter. So it is Newton per meter. And what is the dimensions of force constant? What is the dimensions of force constant? For getting the dimensions of force constant, we will divide the dimensions of Newton, that is M1, L1, T power minus 2 upon meter L1. So this, on solving, you will get, it is M1 L0 T power minus 2. So dear students, for today's, this is about today's lecture. In my next lecture, I will make the use of differential equation to derive the formula for displacement, velocity and acceleration. So in the next lecture, we will derive the expression for acceleration, velocity and displacement of a particle performing linear simple harmonic motion by using the differential equation. Thank you so much. Next time we will meet for the next use of this differential equation. Thanks a lot. Thank you so much.